Time for us to talk about some problems using integration by parts. Now, integration by parts came from the product rule, so it's not a surprise that when we think about applying integration by parts, it's usually to integrals that have two terms multiplying together. And we say, well, what we want to do is take this current integral, we're going to take a derivative of one part, we're going to take an integral of the other part, and look at what would happen if we put those two into a new integral. Would it be simpler? And if the answer is yes, we're like, aha, then that's what we'll do. And we've made progress. It is a different tool, it's kind of new, and with all things which are new, practice is very, very important. So as much as possible, you should be doing these problems on your own first. If you're following along with the video, make use of the pause button. See a problem you like? Pause me. Try it yourself first. If you ever get stuck, I'm here. You unpause me, and we'll talk about the problem. Well, let's begin. So our first problem. Find the integral of x e to the x, integral x e to the x squared dx, integral of x to the fifth e to the x cubed dx. Okay, well, wow, this is 3 for the price of 1. How exciting. Let's go in order. So we'll start with this one. So for the first integral, well, we're looking at this and we say, okay, let's think integration by parts. Because that's what we just learned, right? Okay, well, if we think integration by parts, we say, okay, what are our two parts? Well, we can kind of spot we have two natural candidates, x and e to the x. So, all right, one part we should take a derivative of, one part we should integrate. But which is which? Now, if we look at e to the x, differentiate e to the x, integrate e to the x, it doesn't matter. You're still going to get e to the x. It's an incredibly stable function. So I think the question comes down to looking at x. Well, if we differentiate it, it becomes 1. If we integrate it, it becomes x squared. And we ask ourselves the question, which would we rather have to work with, 1 or x squared? And I think we all know the answer, 1, because that's simpler. So that says, aha, we should differentiate the x, which means in terms of the notation, we'll call the x the u, and the e to the x part of the dv. So our du, well, the derivative of x is 1 dx, and the antiderivative of e to the x is e to the x. All right, well, that's not so bad. So what do we have? We have that this is equal to uv, x, e to the x, minus the integral v du, e to the x dx. And you say, well, wow, that's an integral we can do. See, we start with an integral we didn't know how to do it, but then applying integration by parts, we get to an integral we can do. So the integral of e to the x is e to the x, and of course, on the end you put a plus c. And we're done. Great. We could check our answer because it's an antiderivative. You can always check answers with antiderivatives. You say, okay, what would happen if you took a derivative? Well, if you took the derivative of x e to the x, you'd have the derivative of the first is 1 times e to the x, which would give you an e to the x, plus x times e to the x, because the derivative of e to the x is e to the x, and a minus e to the x. So you see the two e to the x's cancel. We're left with only an x e to the x exactly as we want. Ah, beautiful, beautiful. Ah, life is good. Okay, so one problem down. Let's move to the second one. Number 2, the integral x e to the x squared. Oh, wow, very similar, right? So what happens here? So we have integral x e to the x squared dx. And we start saying, okay, well, we start thinking maybe we'll put on our hats again, right? Our parts hat, so to speak. And, well, does it make sense? See, there's a big difference between e to the x versus e to the x squared. You see, with e to the x, it's easy to integrate or differentiate. E to the power x squared? No. Look, differentiation, no problem. In fact, differentiation is great. But integration is terrible. we don't know how to integrate e to the x squared. Not that we're not, very smart. It can't be done in a nice way. So we say, well, this part we can't possibly integrate. We could differentiate it, but that would mean this part would be the part that we'd have to integrate, which would mean if we were to do parts, the only way we could do it is to make this the part that we differentiate, and this would have to be the other part, that the part we'd integrate. So v would be a half x squared du. Well, that's not so hard. That's 2x e to the x squared. So if you carry this out, you get x cubed e to the x squared, because you multiply, uv. I multiplied the wrong things together. So u times v, that's a half x squared e to the x squared, minus, now you multiply those together, the integral, and a half times 2, those cancel, and you're left with x cubed e to the x squared. And now you look at this and you say, forget it. Hopeless. Hopeless. Why? Look, it's gotten worse. It hasn't gotten better. And so this says we've not made good progress. So now we step back and say, but wait, we are kind of forced, if we're doing integration by parts, to go that route. But wait a second. Were we forced to do integration by parts? You see, we have to be careful, because integration by parts, we're looking at it like, ooh, it's our shiny new toy, let's play with it. But it doesn't mean that it should always be used. We have all these wonderful other options out there. So we should slow down and say, before we do integration by parts, is there something better? And in this case, looking at this, there's sort of a suggestion going on. We see that the exponent here is a function inside of a function. So when you see functions inside of functions, you start thinking chain rule. So, which of course means, for integration, substitution. Okay, so let's try a substitution. So suppose we'll come down here, we'll rewrite it. So you have the integral of x e to the x squared dx, and we're going to do a substitution. U equals x squared, then du would be 2x dx. And we're like, wow, perfect. There's an x dx there. I can just move the 2 across, make it a half du equals x dx. And so, what do we have? Well, this is the integral of the x dx becomes a 1/2 du e to the x squared e to the u. So this is 1/2 e to the u, that's the antiderivative, plus c, and then of course substitute back what u is. So 1/2 e to the x squared plus c. So the moral here, don't rush to do parts. Sometimes things look like they might be parts, but maybe there's a better substitution. And then you say, aha, it really wasn't parts at all. Aha, okay. Well, 2 down, 1 to go. Last problem. X to the 5th e to the x cubed. Okay, so how do we think of that one? Well, let's think about the way we would approach this problem. And suppose we hadn't yet learned about parts. What would we do? Well, one thing we would say is we have that x cubed function sitting inside the e. So we have like e to the x cubed. That really is crying out, make a substitution. So let's make a substitution. I'm going to choose a symbol. I'm going to choose t. We can use any symbol for substitutions that we want. It doesn't have to be u. So t equals x cubed. Then we have what? dt is 3x squared dx. And I say, so close. We have x to the 5th, which has 2 x's, but then there's 3 more. We have 2 for the x squared, but how do we handle the x cubed? And then we're like, oh, wait. Really, we can think of this in the following way. We can say, hey, this is really x cubed, e to the x cubed, and then an x squared dx. So in other words, we broke off two x's to become attached to the dx, because now we say, aha, if we move this 3 across, we see that this is secretly t, e to the t, and then we have a 1/3 dt. Great. Beautiful. So we did a substitution to simplify, and now we say, okay, what do we do here? Well, we look back and say, hold on, this looks familiar, like we've seen this somewhere before, because this is familiar. We've seen this somewhere before. It's right here. And you're probably thinking, no, it's not. This has t's, and that clearly has x's. How are they the same? Well, they're just names. We can change symbols. It doesn't change the underlying results. I could replace the x by any symbol. As long as I replace the x over here by the same symbol, it's still going to be true. So we say, aha, I can come here now using the integration by parts, and I can say, look, this is really 1/3 times t e to the t minus e to the t, and there's a plus c. Now, we're not quite done. We did take the antiderivative, but to finish off, we have to replace t by x cubed. So this is 1/3 x cubed e to the x cubed minus e to the x cubed plus c. And there we go. That's our answer. Now, one thing we should spot right here is to say, oh, it's kind of interesting. We're using substitution and integration by parts. And yes, you see, these are both wonderful, powerful tools. And you're allowed to combine tools together. And oftentimes, you'll see several problems where you're like, oh, it's not just A and it's not just B, it's a little bit of a both. And so you want to get really comfortable with the tools to know at what point do I use this tool, at what point do I use that tool, and how can I combine. Oftentimes, here's how I like to think of it. This is sort of my mindset going to a problem. I ask myself, what can I do that will help simplify my expression? And I do it. And then I say, okay, now I have a simpler integral to work with. What do I do now? So in other words, at every step, you can sort of say, it's like I'm starting fresh. Now, I'm looking at it with new eyes. What's the next thing for me to do? And move forward. All right, great. Well, a nice warm-up problem. Kind of like 3 warm-up problems, isn't it? Well, all right, 3 warm-up problems. So let's move forward and do some more problems. Find the integral, or antiderivative of, cosine of theta times log of secant theta plus tangent theta d theta. What? Okay. Now, here I think this is a good candidate for integration by parts. There's not a great substitution that jumps out. You might say, well, you got the secant theta plus tangent theta on the inside. That could be your u. But you take the derivative of that and you're like, oh, that looks like secant tangent plus secant squared. Does not look like cosine at all. So no, this is not a clear substitution. But there's something else that pops out. If we look at this for a second, we say, hey, log secant theta plus tangent theta, that rings a bell. We've seen that before. In particular, when we go over our table of our 10 functions, which are sort of the most important, log of secant theta plus tangent theta shows up in that table. It's the antiderivative of a really nice function. So in other words, this expression, this has a nice derivative. Of course, it'd be a terrible thing to try to integrate, but it's a really nice thing to differentiate. It's going to simplify. We'll talk about what it is in a second. On the other hand, cosine, whether you integrate or differentiate, it's going to be sine up to some plus or minus factor. So we say, okay, well, since we really don't care what we do with the cosine, and this other piece has a really nice derivative, that's telling us, let's try to do our parts. So we say, okay, this part on the end will be u, because it's going to be the part we differentiate. The cosine will be our dv. That's the part that we're going to integrate. So the integral of cosine is positive sine. Now, you've had a moment to think about it. Do you remember where that log of secant plus tangent showed up? It came from the integral of secant. So when you integrate secant, the result is log secant plus tangent. So if you differentiate log secant plus tangent, you get secant. So that's why we say it has a nice derivative. Okay, so now we say, aha, our integral becomes uv. So, all right, that is sine theta log of, and secant theta plus tangent theta. Okay, so uv minus integral v du. Sine of theta, secant of theta, d theta. Okay, all right, well, closer, a lot closer. Of course, how do you integrate sine times secant? Well, not so clear. You see, oftentimes, sine and cosine work well together, and secant and tangent work well together, but sine and secant don't quite mesh. That's okay. We have ways. And in particular, we say, hey, you know, there's another way to write this. Secant is the same as 1 over cosine. So you really have sine times 1 over cosine. And if you think about what sine over cosine is, it's really tangent. And then we say, whoa, tangent, that's on our list. In other words, it's one of the functions that we know how to integrate. So we're almost done. We say, okay, so we have our first piece still, sine of theta log secant theta plus tangent theta. And the integral of tangent, do you remember that? It's log secant. And of course, a plus c on the end. Now, if you don't like to write it this way, you could also write it as a plus log cosine. That would be equivalent as well, but they're both correct. And there we go. That's our answer. Cool. Wow. See, it looked really like, this is going to look terrible because we have to integrate log of secant plus tangent. But then when we did integration by parts, it was like, whoa, no, we don't integrate it. We actually secretly differentiate it. And it became something beautiful that we could work with. Life is so good. We are so lucky to have such wonderful, fun problems to work with. All right. So let's try another one. Here we go. Find the integral of log of z squared plus 1 divided by z squared dz. If we think about, well, maybe there's a substitution to make, there's only really one candidate that pops out, which is z squared plus 1. And the problem is that the derivative of that would be a 2z dz. It doesn't really mesh well with the z squared downstairs. So let's think about parts. Now you might say, Steve, we're going to run into trouble here because we don't have two things multiplying, we have a division. Well, but really division is just a form of multiplication. So we can rewrite this. So let's write it as the integral of log of z squared plus 1 times 1 over z squared. In fact, let's write it even a little bit more, because 1 over z squared is not quite very calculus friendly. To be calculus friendly, it should be z to the minus 2 power. Now, why to the minus 2? because our rule for how do we integrate something to a power works a lot better when it looks in the form z to something. So, if it's z to the k, you add 1 and divide by the new exponent, right? That's the rule. So now we have to think. Which part do we integrate? Which part do we differentiate? Now, what are our two parts? Well, these are our two parts. And I look at this one and I ask myself, will I rather integrate or differentiate? Or do I sort of not care? And here I say, I have no idea how to integrate that. I don't know. So we're like, probably should be the part we differentiate. So that's going to make this a u. We should come to the other part and say, are we okay with that? We say, well, look, that's z to a power. We know how to integrate z to a power. So yeah, that's fine. That can be the part that we integrate. So let's see. What's our derivative, du? Well, derivative of a log of something, you take 1 over the inside, so 1 over z squared plus 1, times the derivative of the inside. So that would be times 2z. And then there's a dz on the end. Integral of z to the minus 2, well, that would be add 1, z to the minus 1, divide by minus 1. So that would become minus z to the minus 1, which you can write this as a minus 1 over z. Okay, so now where are we at? Well, we are going to do u, v. So that'll be minus log z squared plus 1 over z minus the integral v du. So minus 1 over z times a 2z over z squared plus 1 dz. Okay, sounds good so far. Well, look, we can do some things to simplify. So minus log z squared plus 1 divided by z. Minus makes a plus. 2 we can pull out. So we can write this as a plus 2. The z's cancel, and we get 1 over z squared plus 1. Like, what? 1 over z squared plus 1? That's awesome. We love that integral because it's on our list. It's on our list. In particular, it is the following function. So we still have that minus log z squared plus 1 over z plus 2 arctangent. What a cool function. So arctangent of z, and then always, of course, don't forget a plus c on the end. And there you go. It's kind of cool because you don't look at the problem and say, this is an arctangent problem. But as the problem evolves, you're like, oh yeah, it does show up as an arctangent because you get a 1 over z squared plus 1. Wow, cool. What a great answer, a beautiful, beautiful answer to a really fun problem. Good, well, let's keep the fun going. So here we go. Find the integral x to the a log of x. And this is for any a not equal to minus 1. Now you might be thinking, why do you say not minus 1? Well, actually, we can talk about that really quickly. In fact, what happens if a equals negative 1? Well, what you really have is x negative 1 is the same as 1 over x, right? X minus 1 is 1 over x dx. And lo and behold, this becomes something really clean. If we do substitution, see, if this is u, then this part would be du. So this would become the integral of u du, because the derivative of log x, 1 over x. So this becomes a half u squared plus c, which would make it a half log of x squared plus c. Now be careful here. Pay attention to your parentheses. Natural log of x, the quantity squared, that square does not come down because that square is not inside the natural log. It's outside the natural log. So be careful with your rules. It's kind of tempting to say, oh, I could just bring the 2 down. No. Because the 2 is not on the inside. Okay, so that says, hey, if a equals -1, substitution and life is good. But what if a is not -1? Aha, well, that's our problem. So let's try it out and see what happens. So we look at this and say, all right, suppose we have the integral of x to the a natural log of x. So what can we do? Well, what we can do is say, okay, there's 2 parts. Let's try integration by parts. Looking at these, one part we have to integrate, one part we have to differentiate. Now, looking at these, I can say, I don't want to integrate log x because I don't know how to integrate log x. I haven't learned it yet. So I better differentiate that part. Okay, so that makes it, so we need to have that be u, which means the other part is dv. But we know how to integrate x to a power. So what does happen? Well, du becomes a 1 over x dx. And here, x to the a, here is where you need the fact that a is not -1. Because what will the integral become? The integral will become, you add 1 to the power, a plus 1, and then you divide by a plus 1. See, if a were -1, you'd run into troubles here, but we're assuming a is not -1, so no troubles. So what do we have? Well, now we have an integral of uv. So we have x to the a plus 1 natural log of x divided by a plus 1. So that's our uv minus our integral v du. So that's a 1 over a plus 1 x to the a plus 1 times a 1 over x dx. And now this new integral, it's actually easier to work with. We say, hey, look, I can cancel off one of the x's. So I can say 1x here cancels with the plus 1. So what you really have is the integral of x to the a again, because we did the integral of x to the a already. So we have x to the a plus 1 times the natural log of x over a plus 1. That's our first term. Minus, and here we'll get 1 over a plus 1 squared x to the power a plus 1. Because that's what the integral of x to the a is. See, there's a second a plus 1 that comes down in addition to the one that's already there. And of course, at the end, it's an indefinite integral. Don't forget, plus c, plus c. And we're done. Let's do a special case. And I think that this is good that we should mark this special case. What if we had a equals 0? Well, what does that mean? Well, it means we have the integral of x to the 0. So that would become simply the integral of natural log of x. So what do you get? Well, you get x to the 1 times natural log of x divided by 1. So that's x log x minus 1 over 1 squared, which is 1, x to the 1. So x log x minus x plus c. So there's sort of a nice special case for reference. So now we say, hey, we could integrate log of x. But really the secret is it's just an integration by parts, and we know how to do integration by parts now. It's in our toolbox. So many things. So I don't necessarily recommend memorizing the integral of log x. I mean, it's not the worst thing to have to memorize. I think it's just easier to memorize the process, because it's very likely if you ever have an integral where you have a log x, it's almost just as fast to just quickly redo it using integration by parts. All right, well, let's try another problem. All right, good. So we have this function, and well, we don't have very much. It's g, but we know a couple of things. we're told g of 0 equals 3, g prime of 0 is negative 1, g double prime of 0 is pi, g of 1 is 5, g prime of 1 is 2, and g double prime of 1 is 1. And we're asked to find the integral 0 to 1, so a definite integral, x squared g triple prime of x dx. Wow! Amazing! Now you might say, cool, how do we find g? And the answer is, we don't. We don't have enough information to find our function g. It can't be done. It can't be done. So you might be saying, okay, is it even possible? Well, yes. I will say technically there's another assumption that this problem doesn't explicitly state, which is, oh, by the way, g is a function which you can take 3 derivatives of, but we know what they mean. So we won't give them too hard a time about forgetting to mention that. So looking at this, we say, okay, we want to make progress in figuring out what this integral is. And we have an integral which involves the third derivative of g, but we have no information about the third derivative of g, which means we probably shouldn't try to figure it out by actually coming up with an explicit antiderivative. We should probably think about what are the tools. So we can write down and say, all right, well, it looks like a parts problem because we have two functions being multiplied. And we have to ask ourselves the question, which parts do we want to integrate? Which parts do we want to differentiate? So when we look at this, we say, hey, this part right here, we can integrate. And it doesn't necessarily feel that way, right? But think about it. If this is the third derivative, what's the integral of the third derivative? The integral of the third derivative is the second derivative. So that's our dv, g triple prime, v becomes g double prime. On the other hand, if we think of the x squared, if we make that u, then du is 2x dx. It actually simplifies. So this is great because it says, hey, this part, when we integrate, we got g double prime, and we have information about g double prime. And this other part, when we differentiated, it became something simpler. It's a win-win. It's a sign we're probably on the right track. I love it when we're on the right track. It's a wonderful feeling. Okay, so what do we have? We're going to look at u, v, so that's x squared, g double prime of x. And because it's a definite integral, we have to evaluate that from 0 to 1 minus, okay, the integral, 0 to 1, of v du. So I'll write that as 2x g double prime of x dx. Okay, good. Well, we've made some progress. Lower exponent, lower derivative. Win-win. Okay, but we're not there yet. So we probably have to do integration by parts again. Now, this comes back to one of the things that we mentioned when we did our sort of overview of the topic. If you're doing integration by parts multiple times, you have to commit. In other words, you have to have sort of a consistent part being your u and your dv. So now we're not going to be humming and hawing about, well, which part is our u, which part's our dv? We don't have a choice because we already made it. We have to stick with our choices. So whatever was our dv before needs to keep being our dv. So that became the g double prime. So that is going to be our dv again, which means that our v is g prime. So the 2x came from what was u before, so it's our new u now, which means that our du is 2 dx. Okay, so now let's update. What do we have? Well, we have x squared g double prime of x from 0 to 1 minus, okay, now this is one of our first chances to sort of point out the pitfalls of integration by parts, the minus sign. And if you do it integration by parts multiple times, a lot of people miss the minus sign. So that's why I'm pausing to make it very dramatic, like, wow, the minus sign. It's amazing, because we definitely don't want to miss out on anything. So I'm going to be careful here and use parentheses, because that will help me make sure I don't miss any minuses. So u, v. So that'll be 2x, g prime of x. Evaluate that from 0 to 1, minus the integral v du. So that'll be 2 g prime of x dx from 0 to 1. Okay, now what do we have? X squared g double prime of x from 0 to 1 minus, distributes in, so minus 2x g prime of x, 0 to 1, minus minus makes it a plus. See that minus minus, that's what I'm talking about. Remember, that goes through. And I've seen so many people lose points because they forgot about that minusing distributing. Okay, do we know how to integrate g prime of x? And the answer is yes. We do know how to integrate g prime of x. It is g of x. And now we're like, perfect. We found our nice antiderivative. So the last thing for us to do is to plug things in. So what happens? Well, we plug in 1. We're going to get 1, g double prime of 1. So that's g double prime of 1. And then subtract 0 squared times g double prime of 0. Goes away, because I have 0 times something. Okay. Minus 2 times 1 times g prime of 1. So minus 2 g prime of 1. Then plug in 0. 2 times 0 times g prime of 0. Goes away. All right. Plus 2 times g of 1. And then subtract 2 times g of 0. So here, it doesn't go away, so we've got to write it down. So last thing, and then we're done, is we just have to look these up. G double prime of 1 is where? There it is. It's 1. Okay, so we get 1. 2 times g prime of 1. 2 times 2 makes that minus 4. 2 times g of 1. 2 times 5 is plus 10. Minus 2 times g of 0. So minus 2 times 3 is minus 6. So 1 minus 4 plus 10 minus 6 gives us a final answer of 1. Of course, you're like, what? All that work for 1? Yeah, well, sometimes you got to do the work, right? You got to do the work. But hey, it's kind of fun. Even though it feels like, do we have enough information? We actually do. In fact, we didn't even use all the information, because it turned out, for instance, g double prime is 0 and g prime is 0 never entered in to the computation at the end. So we could have made do with even less information. Cool. What a fun problem. What a fun problem. All right. Well, I think we have time for one more. So let's make it a good one. And I think this one's going to be a great one. Oh, yeah. So here we go. So find the integral of e to the power ax sine of bx. So we're thinking of a and b should be thought of as numbers. And so we were looking for, how do we find this antiderivative? All right. Well, we kind of have a feeling, okay, they're very different, exponentials and sines and cosines. It turns out they're actually not that different. They're very closely connected to each other, almost as if they're the same function. Well, that's a great story which we'll tell in the last part of the class. But that's for another day. But the question is, okay, so how do we approach this? And it feels like a good candidate for parts, because you have two things multiplying together. So if we think of these as our two pieces, all right, which part should be our u, which part should be our dv? And we say, okay, well, look, well, e, it doesn't really matter whether we integrate or differentiate. we're still going to get like something that looks like e. Sine, it really doesn't matter whether we integrate or differentiate, we're still going to get something that looks like cosine. And so at this point, you're like, it doesn't seem to really matter, right? And the answer is, nope, it doesn't. So we just pick one, and then we're happy. So I'll choose u to be the e to the ax, and the dv to be sine of bx dx. It could have been the other way, but we have to make a choice. And remember, once you make a choice, you stick with it. So what is our du? Well, a e to the ax dx. That's pretty straightforward. The integral of sine of bx, what would that be? The integral of sine is negative cosine. Ooh, okay. So negative cosine bx. And then remember, we have to account for that b on the inside, and we do it by dividing by b. Okay, so there we go. All right, so now integration by parts. What does that tell us? It says the following, that this is going to be equal to, let me grab a nice color here, uv. So I'll put that as minus 1 over b e to the ax cosine of bx. All right, good. All right, but we're not done yet. Minus the integral of v du. So minus the integral of, and we'll write it as a e to the ax minus cosine of bx over b dx. Okay, so let's clean that up a little bit. So what do we have? We have minus 1 over b e to the ax cosine of bx, and we can pull out the constant. So a is a constant, and a minus 1 over b is a constant. So it makes plus, because minus minus is a plus, a over b integral e to the ax cosine of bx dx. Say, well, okay, we started with an integral that looked like e to the ax sine bx. Now we're to an integral that looks like e to the ax cosine bx. What should we do? Well, integration by parts is a technique so nice. Let's do it twice, and let's see where we end up. So let's try it again. Now, we don't have to think about which part do we make which, because our rule of thumb is once you make a decision, you stick with it. So we're going to keep going. So in other words, whatever was acting like our u before continues to act like our u, and similar for the dv, which means the e to the ax, that's our u, our cosine bx dx, that's our dv. So what do we have? Well, I'm going to put it above here just for space purposes. So we get, similar as before, du is a e to the ax dx, and v, well, a little bit nicer, because the integral of cosine is now positive sine, so we'll end up with sine of bx, but we divide by b. Okay, so let's put this together. What do we have? Copying what we wrote down before, so we have a minus 1 over b e to the ax cosine of bx, and then a plus a over b times, I'm going to use parentheses here. So the parentheses, you can imagine I have parentheses here. So I'm going to remember that the a over b distributes through. I got to be careful. This would be a place where you might potentially lose a constant if you weren't paying attention. But we're going to pay attention because we're not going to lose anything. Okay, so what do we have? U times v. So that'll be e to the ax sine of bx divided by b, and then minus the integral of v du. So that'll become an a e to the ax sine of bx over b and then dx. All right, well, okay, what does that say? Let's expand. So when I say expand, multiply this a over b through. So we have minus 1 over b, e to the ax, cosine of bx, plus, here we'll have an a over b squared, and then it'll be e to the ax sine of bx. And now there's going to be an a over b as well, so that'll become minus a squared over b squared integral e to the ax sine of bx dx. Now, at this point, you're probably thinking, we might be here for a while. Should we go pop some popcorn or something? Because you're starting to feel like you're going to get stuck in a loop here, Steve. Aha, we could get stuck in a loop, but this is our great what does that mean? Well, we look a little bit closely at what we have, and we say, hey, what do you notice? This part looks similar to this part, but they're actually not the same because of this coefficient. So it's not the case that they would cancel if we were to move things across. They'd actually combine. So what does that tell us? Well, what we'll do is we'll move this across and combine together. And so what we really have is the following. We have this integral plus that integral, which makes it a 1 from this one, plus, because when we bring it across it, we add a squared over b squared, which is from that, times the integral of e to the ax sine of bx is equal to minus 1 over b e to the ax cosine of bx plus a over b squared e to the ax sine of bx. And do I need to put any other thing here? This is where we separate the calculus, I don't know if I want to say the calculus kids from the calculus tweens. I don't know, whatever you want to say. There is something else that needs to be written down here. And what we need, plus c. Now you're probably thinking, whoa, hold on. Where did that come from, Steve? It wasn't there in the previous line. It was kind of there. This comes back to a discussion. These integrals are antiderivatives. But remember, antiderivatives are unique up to a plus c. So this antiderivative doesn't have to be the exact same as that antiderivative. They can differ by a constant. And so when we moved them over and combined, we had to say, oh, wait, hold on, they could be off by a constant. That's where that plus c came from. Okay, so we just didn't write it down for the sake of writing things down. If we look at this piece here, we're saying, wow, we're really close. We just want to get rid of this part. So what we're going to do is we're going to move that across. Now, we'll do it by multiplying by the reciprocal. Notice that this is really the same as, let me see if I can move this up a little bit, b squared plus a squared over b squared. So when we move it across, you can imagine that we multiply everything times b squared over b squared plus a squared. That's how we're going to move it across. So once we've done that, we're going to get our final answer. And good, because we're running out of space, so we better be getting to the point where we get our final answer. So our conclusion is the integral of e to the ax sine of bx dx is, when we multiply here, notice that we get a b to cancel with the b. So that'll be a minus b divided by b squared plus a squared times e to the ax cosine of bx. Now, when we come to this term, notice that the b squareds completely cancel. So we're going to get a plus a over b squared plus a squared e to the ax sine of bx. And now you're thinking, aha, now we're going to have something hard to write down, but we're going to write down plus c. And you're probably like, what? Really? Why isn't it c times b squared over b squared plus a squared? There's one other principle that comes into sort of play here. C represents an arbitrary constant. If you add two constants together, you get a constant. So we can merge constants. If you multiply a constant by a constant, it's a constant. So in some sense, you can think of C as like a constant sponge, absorbing other constants as is convenient. So it's still a constant. So that's why we simply write plus C. And that's it. That's the actual integral. We're done. So this is a case where we did integration by parts twice. What we ended up was something which was almost the same as what we started with, but not exactly, so that we could combine it and then move a constant around. It's a really, really beautiful example of what can happen. In some sense, it's a little bit specialized. This doesn't happen very often, but it does happen in a few cases. So it's nice to be aware of that possibility. So this says, you might not get stuck in an infinite loop. You see, if you ever do integration by parts and you get something that looks like what you started with, you have an escape button and life is good. What an amazing integral. And if you're in doubt, just take the derivative and you can check it does actually work. In other words, the derivative of the right-hand side will produce e to the ax sine of bx. So cool. Wow, what a great tool. So keep practicing. It is a marvelous tool. It's great fun. And I hope you enjoyed it. And I hope to also see you again, right? See you soon.